Hello everybody, my name is Paul Abernathy and welcome to part 3 of a multi-part series on transformer calculations. Now, on today's episode, we're going to talk about conductor sizing, both primary and secondary. But today's episode, we're going to keep it concise to a generic value of what we calculate for these conductors. And then you're going to kind of see how we can apply something called tap rules. Now, we're not going to talk about secondary conductor rules that are found in 240.21c. That's for another episode. Today, we're going to talk about general sizing, as if you didn't know anything about tap conductors. And then we're going to talk about the tap rules that are afforded you in 240.21b3. And that's where we can actually tap a feeder and results in smaller conductors that are not protected at the point of the tap at their ampacity. And that's a whole understanding of what the taps conductors are all about, okay, and what these tap rules are about. So don't worry, we're going to cover all that. Before I get into that, I got to remind you, if you don't know how to calculate the primary and secondary current ratings of a transformer, you need to stop right now and go back and watch the part 1 of this series. If you don't know how to size the primary and secondary overcurrent protection, and that is designed to protect the primary and secondary of the transformer and not the conductors, although it might ultimately protect the conductors, you got to go back and watch part 2 because that explains the primary and secondary protection rules, okay, that are in 450.3 of the NEC. Okay, so do that now if you haven't done that. Because in part 3, we're going to strictly deal with conductors and the nuances of that. And we're going to talk about primary, we're going to talk about secondary, and we're going to talk about some of the tap rules that are associated with both. And it gets pretty intense because we're dealing with tap rules up to 25 feet. And it could be a situation where you need to do an installation where you have to have longer secondary conductors and you need to know these rules. You might have an application where you've got a feeder that's going to supply multiple transformers and you want to know how to apply this rule if you're going to tap a feeder. It might result in smaller conductors to that primary. And you have to understand how to apply these rules so you don't get in trouble by your local AHJ or create a safety concern. So we're going to cover all that in this episode. All right, now there's some givens that we're going to talk about, and I'm going to remind you of those. We're talking about a 75 kVA transformer. It is a delta Y configuration, 480 volt primary, 208 120 Y secondary. Okay, we have already calculated out, and hopefully you'll watch series part 1 of the series. We already know that the primary current rating of this transformer is 90 amperes. The secondary current rating of this transformer is 208 amperes. We've already calculated out the primary overcurrent protection, which we could have gone up to 250%, but we chose not to because we're going to protect the conductors at 125%. So we wanted to do dual duty here. We want to protect the primary, plus we want to protect the primary conductors also at their current rating. All right. So their ampacity values. So if we had to use the 250% allowance in 450.3b, then we would have arbitrarily been required to have a larger primary conductors than necessary to handle what we were dealing with. Okay, so, and I am going to show you an example where the 250% can be beneficial. If any of that confused you, you didn't watch part 2 of the series. You need to go back and watch it. This is a multi-part series, and you need to watch them all in succession in order to truly get the best value out of the video, okay? All right, so we sized the primary at 125%, which corresponds in us sizing our primary conductors at 125%. And we're going to see if that actually protects them at their ampacity. We're also going to look and see what about calculating the conductors basing on the tap rules as well. Because what we're going to give you is not only exam, what you need to know to pass an exam, but real world. We're going to talk real world scenarios here in this presentation. So let's go on and get started and let's look at the base graphic and kind of rehash some things. All right, so here's the base graphic. Oh, here it is. So what we know is in episode 1, I tell you how to calculate the primary and secondary. If you're coming into this video and you want me to do that again, I'm not going to do it because you need to watch part 1 of this series. But we calculated 90 on the primary, 208 on the secondary. We calculated 125 amp primary overcurrent protection, and we calculated a 300 amp secondary protection. And that is based on 125% of the primary current rating here and 125% of the secondary. Now, we could have gone up to 250% here on the primary, but we chose to not do that. You need to go watch episode 2 and understand why we did that. Okay, we'll probably rehash that a little bit here, but you really need to understand that. Okay, so first things first, we want to size these conductors. Okay, since this was 125 amp, and we're not going to apply any tap rules yet, we're going to show you how this works. So I got to have a conductor that can be terminated onto a 125 amp overcurrent device. So what I'm going to do is I'm going to code, and I got to find a conductor that can terminate on a 125 amp device. Okay, well, let's go to the code, make it simple. Again, the 90 amperes is the actual primary current. I could size this conductor if it's non-continuous loads and continuous loads aren't being taken into consideration and all that kind of goodies, then I could size this at 90 amps. But if we're not thinking of any tap rules yet, I don't want to spill the beans to you yet. If I'm not thinking about any tap rules, then if I were to look for a conductor that's rated at 90 amps, then I couldn't terminate it on a 125 amp device because it's not protected at its ampacity. Because under tables that are in 240.6a, and if you don't know what that is, that's the table that lists all the standard overcurrent devices that are available, standard breaker ratings. There is a 90 amp device rating available. So if the conductor is rated at 90 amperes, then I would choose a 90 amp rated device. Okay, and that's what I would choose for whatever it would be. If that conductor has a 90 amp rating, let's say, then I couldn't terminate it on a device that's rated at 125 amps. So in order to get a full understanding of this, let's go back and look at the ampacity table so we can really grasp values now. Now, this is a good time for me to remind you that if you want to know a little more about adjustment and corrections and conductors when they don't meet the 30 degrees C or 86 degrees Fahrenheit, that's the values given in this table, then you need to go back and watch my video called Derating Demystified. Now, in this example, in most all of your exams, you're going to be given the fact that the terminals are going to be rated at 75 degrees C. This is not an episode on terminal limitations and 110.14c. You need to watch the Derating Demystified, and I'll explain everything you need to know about terminal ratings and limitations and all these goodies that comes to conductor ratings, the -2s and all that. Hopefully you know what that is. Also, for an exam, we always want to assume copper, unless somebody states otherwise prior to you starting your exam. So assume copper. Okay, so what did we say? We needed a conductor that is good for at least 90 amperes, because that's what our primary current rating of our transformer is. So here's one for 100. That's at least that, and it's a 3. So that would be a 3 gauge. So I could write that down. So we have a 3 gauge. It's good for 100 amperes. Okay, so that's a 3 AWG. Now, if I wasn't assuming any tap rules at this time, what would I have to protect for this conductor to be protected at its ampacity? Well, I'm going to go to 240.6a. Oops, went too far. All right, here we go. Here's your standard rated breakers. And incidentally, this table the format is new. These standard rated breakers aren't new. This N says that this is new because it's a new table. Usually they just were listed 1 comma, then the next one comma, the next one comma. But here the table kind of makes it a little easier to understand the format. So I do have a 100 amp breaker. So since 100 amp is available, I am not permitted to terminate a conductor rated at 100 amps on a breaker that's rated for 125 amps. That would be a violation of 240.4 of the National Electrical Code, is protecting a conductor at its ampacity. Okay, so I wouldn't be able to do it. Now, me and you both know that the primary current of that transformer is only 90 amperes. Okay, we both know that. But there is no allowance in 240.4 that says, like we do with motors, which says that, you know what, I could have like in a motor, I have the primary, the short circuit and ground fault protection under 430.52 could be rather large, compared up to 250% for an inverse time circuit breaker. It could be up to 250%. And so the conductors could be rather small, but the breaker might be rather large. You don't get that same kind of allowance for transformers. So without that allowance, I've got to protect the conductor at its ampacity. Now, the only allowance that I'm going to get here is the ability to use the tap rule. And you're going to see that when we get to it. But right now, we're not talking tap rules. We're just looking at the code. All right? And we're taking what we've been given based on to this point up to part 3 of this series. All right, so let's go back and look at the presentation. So this was a 125 amp rated, okay? And these conductors were, we thought that they would 3 would be okay, but that's not true. Then protect them at their ampacity. What do I got to do? Well, I could go up to the next size and see if that is going to work, okay? All right, so let's go and see what that would be based on what that device would be. So let's go to the code. And that would be, let's go back to the ampacity values. And we're going to go down here. We're staying in the 75 degrees C. And okay, well, 115. All right, well, 115, since it doesn't correspond, then when you, and so we got a conductor, if we choose this one, which is a 2, then let's go back and look and see if it's okay for that 2. And I'm sure it is. We were just there. And, oh, there's no breaker that corresponds to 115. So, in accordance with here, 240.4b, since the ampacity of the conductor, which in our case was 115, doesn't correspond with the standard rated breaker or fuse, then I can go up to the next available size, as long as it doesn't exceed 800 amperes. All right, so that's what we did. So let's scroll back down. So it didn't correspond, so that's where, so it can be protected at a 125. So that's perfect. So if you go back and look here, then I can have a 2 gauge conductor, that's a 2, AWG, and it can terminate on a 125 amp rated overcurrent device. Again, assuming no tap rules right now. This is all we're doing, just sizing conductors based on what we know. So that's what it would be, all right? Now, if this was rated at 250%, then that would also be a problem right there, because I still would have a conductor that wouldn't be able to terminate on that device. So that's the problem with going all the way up to 250%, which is you're allowed to do, but most practical reasons, unless you have multiple transformers, that's not what you're going to do. So most design people in the real world are going to be maximum of 125%. Now, you know how we did it one size and then jump to the next size to see it was okay? The easiest thing to do is to do the primary protection at 125%. And you know that if you have continuous loads, then you're going to do at the worst case scenario is you're going to take them all at continuous loads and do the conductors at 125%. And more often than not, that primary protection is also going to protect the conductors as well. Okay, and so we're trying to do double duty here, letting one device serve the protection of the conductor as well as the primary. Okay, now in the rules for the 250%, that might not be the case. Whereas I might have something that protects the primary at 225% if it was only one transformer, but I might need another device that actually protects the conductors, even though those primary conductors are only going to see 90 amperes probably, because that's what the primary current rating of that transformer is, very limited. Okay, so keeping that in mind. All right, now could it potentially see more? It might on an inrush from the secondary, but this is what the code does for our sizing. So just kind of keep those things in mind. All right, and so we have to protect those conductors. Now, let's look at the secondary based on what we know. Because right now we haven't done anything right now. Right now, based on what we saw in the graphic and sizing conductors on the graphic only, we need a 2 gauge for the primary side. Okay, so now let's do the secondary. All right, so secondary based on what we know, it's 208 amps from the secondary current rating, and we sized this overcurrent in our previous video, which is part 2. This was 300 amperes. So I need a conductor that's going to terminate, because this right here is going to limit the load to 300 amperes. We have to assume that they did a load calculation. It's probably much less than this anyway, but since it's terminated, and you're going to see that requirement also in the tap rule, that this is 300 amp because we use the maximum size. Okay, we get our biggest bang for our buck, even though we know that this transformer only has a 208 amp secondary current rating. We went to a 300 amp device protecting this panel board. Okay, so these conductors here, just based on no tap rules right now, based on what we know, we're going to size these conductors to handle 300 amperes. So what size would that be? So let's go to the code, and we're going to go to 31015B16 again. And we're going to, all things staying the same, we're dealing with 75 degrees C, we're assuming copper, and I need a conductor that's good for 300 amps. Well, some people will ask at this stage, well, why can't I use the 285, and if it doesn't correspond, I go to the next size? Well, that's because you're not allowed to do that. And why aren't you allowed to do that? Remember, we're doing taps right now. So I want to show you where it says that in 240.4b, 240.21b. I don't know why I said that here. So we're dealing with a feeder tap right now. Okay, let me get back to B. So here's what we're dealing with, B. Okay, and notice it says the provisions of 240.4b shall not be permitted for tap conductors. Okay, and in our case here, we have tap conductors. All right, and so even in our rule down here, right here, we're dealing with tap conductors that are supplying it now. All right, so if we're dealing with the tap rule, we can't do that. We can't utilize the next size up rule. Now, even if we're dealing with secondary conductors, all right, and that is going to be under this one, C. It also reminds us that the provisions of 240.4b shall not be permitted for the transformer secondary conductors. So we can't utilize the next size up rule that we did for the primary side. Okay, so what that means is right here, these conductors, we can't use the next size up rule. So when it came to the ampacity, that 285 was not going to work for us. So we got to go back to the code, and we'll go back to 310.15b16. And right here. So here's where my conductor is. So that's not going to work. That was a 300. So we're going to have to go to the next size, which is 310, which can easily handle 300 with 10 amps to spare. And that is a 350 kc mil. All right. So we go back to our presentation. So this right here, conductor, based on what we know, remember, we haven't done any tap rules yet. Here, this would be 350 kc mil. And this would be a 2 gauge, and those conductors would be considered protected by this. This would be the limiting the current to 300 amperes, even though there's probably a calculated load is not going to be anywhere near that because this transformer output is only 208 amps. So, but at any rate, we're just basing it on the calculations here for exam. Okay. Now, in the real world, the transformer would be sized based on whatever the load was at the engineer's size. So they wouldn't necessarily pick a 75 and then try to size everything else. They would do what the loads are that they need for this transformer and what size panel they need, and then they would choose the transformer and see what the secondary was on that transformer and then see what they needed, and that's how they would work it together. So they kind of work their way backwards. When we're in exam, we're usually going to be given the transformer size and things like that, so we're really working from the transformer out for a lot of these little questions. Remember, on an exam, they're really not going to get 3 and 4 cycles deep into the question. It's really going to be very simple. What's the maximum overcurrent protection for the transformer? What's the maximum secondary protection? All those type of things. And so remember to read the question because they're going to deal with those focus points. Okay. Again, always assume copper unless they say otherwise. And remember terminal limitations. They're usually going to give you what the terminal ratings are so that you know to stay within the 75. Okay. It wouldn't be fair otherwise. Okay. So back at the graphic. So we know in this case, based on no tap rules at this point, we know that these conductors, based on this 350 and this 2 gauge. Okay, now let's go and move into the tap rule. Now on this graphic, we're looking at 240.21 B3, which is a 25-foot tap rule when it comes to tapping a feeder. Okay, now there's 2 different types of tapping for the feeder application that people need to be aware of. Here, this is an application where it's actually tapping a conductor. Okay, so this is a feeder conductor that's connecting all the way here to this breaker. Okay. In this example here, I could also use this tap rule. If I wanted to say that this was a tap conductor and this is a feeder location, and I could apply the tap rules here as long as it doesn't exceed the 25-foot tap rule, and that's 25-foot primary plus secondary tap rule. okay, then I could apply it. So this plus this could not exceed 25 feet. Okay, and we're going to look at how that would work. Now, if I wanted to size that like we did originally, based on whatever the loads were, and whatever it's going to be terminated, then that's fine. I could do that. But I'm going to show you how the tap rule might save you if you size these conductors too small. Now, here's the first thing I'm going to tell you. There are many people out there that will argue that this tap rule only applies when you're tapping a conductor. But it doesn't say a wire type conductor. It just says a conductor. The load terminals on that device could be considered taps. Okay. And I can do tap rules from there. Okay. Now, I can't do them and then tap them again because I'd be tapping taps, and I don't want to do that. That's the tap conductor that's coming out. And so as long as it terminates into the overcurrent protected device, you'll see that in a minute, then I could apply those on the load side. Now I could have a device that has multiple lugs, and maybe it's feeding one panel here or one transformer here and one transformer over here. As long as that breaker is sized properly, that is going to be our primary overcurrent protection in this case for this tap rule. As long as it's done right and all the tap rules are followed, there is no harm, there is no foul. But just remember, there's two different ways to consider it. I could literally tap a conductor because maybe I need to go further into the building with these feeders before I actually implement these 25-foot limitations. Or I'm right next to the breaker and I want to apply them right here in the same room, then maybe I want to do that. And say, so remember that. This is controversial to many people, but a lot of people think the tap conductor fully has to just tap a conductor of the wire type. It's not true. Not true. All right, you can agree to disagree, but again, this application right here could be utilizing the tap rules, or you could size them like we just did originally. So we're going to do it and show you how you might use a tap rule if you get in a pinch, and these conductors happen to not be rated as a 2 gauge, or maybe even they might be the 3 gauge, because maybe you're just sizing it to the 90 amperes of the primary current rating. We're going to show you how that works out. Don't worry. Don't worry. Okay. So I've got 2 examples here of this tap rule. We're going to focus on this one here on the right first. Okay. So this is our service panel. This is a service conductors coming in. There's just your main overcurrent protected device here. Again, these conductors are protected against overload, not short circuit and ground fault protection. This is overload. Everything on the load side of this one's going to be protected by overload, short circuit, and ground fault protection. Okay, overcurrent device there. And here's your feeder breaker, and this is a feeder coming out into a wireway. And this wireway, these feeder conductors are being tapped in this wireway. Okay, so this is the most common application for this tap rule. All right, so let's kind of throw some things out here so you can just basically understand. So let's assume I know what the load is on these transformers. The engineer has already calculated the loads and everything, and they know they're good. So they sized this device right here at 250% of, these both were 75 kVA. So 250% of the primary current rating. Okay, so this is 90 ampere primary current rated. Remember what we said, you take any one. If you watched part 2, you get this. So it's 90 times 250%, and that results in, let's go on and do the math. I'll do it with you, but it should be 225 amps. So it's 90 times 2.50, it's 225. So this device is 225 amperes. These conductors, these feeders, are sized to handle 225 amps so they can be protected. So I sized these at a 4-aught. If you looked at 31015B16, you'll see that these are going to be rated for good for 225 amperes. So this is copper, and we're talking about copper and a 4-aught conductor. Okay. Now, so these are done. Now, I'm going to do these tap rules. Now, if we went based on our first calculation we did, not assuming any tap rules, let's just do it based on what we assumed first, that this was 2 gauge and this was 350. Let's do that first. All right, so what are the rules for this tap, and what do the taps mean? That I can tap a feeder without any overcurrent protection at the location of this tap. When it comes to transformers, it means that I'm using this device here as my primary protection for the transformer, and this device is my secondary. But I have to meet all of these rules, and these conductors have to be sized at least based on the minimums that are allowed in this rule, but they still have to be sized to handle whatever the loads are that we calculated first. Okay, and you're going to see how this works. Don't worry. All right, so let's go and size these conductors. We already said that they're 2 gauge, and this one was 350 kc mil, and these are 4/0. Okay, and this is a 225. So let's go on and apply some rules here. Number one, let's look at these conductors first. It says conductors supplying the primary of the transformer, that's these right here. That's what these are. Have an ampacity at least a third the rating of the overcurrent protected device protecting the feeder conductors. Okay. Well, whether or not I was connecting onto these like we said here as feeders, it doesn't matter. You can assume what size conductors they would be, or you just have to look at what size this device would be. But in our case here, we do have conductors and we do have the protection, and it is at 225. So what we want to do is take that 225 and we will divide it by 3 because we're dealing in thirds, and that is 75 amperes. Now, do I have conductors that are going to be at least rated at 75 amperes? And the answer is absolutely. We picked the 2 gauge, and that was good for 115 amperes. So does that exceed 75 amps? Most certainly. So we're good here. Incidentally, if we had done this based on these being only calculated to be 100 amps to handle the 90 amp load, if it wasn't, for example, any continuous loads involved, it was just the rating at 90 amperes, which is what the primary rating is, and we decided that that would be a 100 amp breaker, or a 100 amp rated device. It wouldn't work in this example, but will it work in this example? Well, yeah, because the conductors, even a 3 gauge was good for 100 amps, and that is at least greater than a third of this rating, which was 75 amps. So even a 2 so far would work in this rule if you want to utilize this tap rule. That might save your butt. If you made this, you tried to utilize this, and some inspector comes in and say, oh, this conductor is not protected at its ampacity. Then you say, oh, but I want to use the tap rule here. Then you'd be okay if this was only rated for a 3 gauge conductor instead of a 2. See how that works? Can really save your butt. All right, so here we're using the wire type, so just stick with me. So these were rated at 2 gauge, which is good for 115, so we're good here. Second rule, it says conductors supplying the secondary of the transformer, that's these right here, right there, shall have an ampacity not less than, of course it could be more than, but it can't be less than the primary to secondary voltage ratio multiplied by a third of the overcurrent device protecting the feeder conductors. Okay, well in this case we actually have conductors here. All right, so again, it doesn't say wire conductors, so again it could be the lugs or whatever, but anyway, we don't want to go there yet. So here we got a feeder, and we know that this was 75 was the third, so we already know that value. So what's the deal with this primary to secondary voltage rating? What do you do there? Well, it's pretty simple. You take your calculator and you take the primary, which was 480, and you divide it into the secondary, which is 208. And that's going to give you 2.307, and you're going to round that to 2.31. And that's your primary to secondary ratio, voltage ratio. Okay, so what did the code say? It said take the primary to secondary and multiply it, the ratio, and multiply it by a third of the overcurrent protected device protecting the feeder, okay, or whatever that value is of that device. And so in this case, that would be 2.31 times 75. And that is 173.25. You write that down, 173.25. Now, based on what we did earlier, were our conductors have an ampacity of at least 173.25? And of course the answer is yes, because we chose 350 kc mil, which was good for 310 amperes, right? So we are good to go. We easily meet item number 2. But let's do a little thing here. What if the engineer had calculated this load and he only wanted to have a 200 amp panel here? Okay, hang with me now. I'm just going to throw some extra stuff in there. Now, we know the primary current on here was 208 amps, and we know that the maximum primary, secondary rated, secondary overcurrent device, the secondary current has to be protected. The secondary windings had to be protected at not more than 125%. So that's where we got 300 amperes. But what if we only have a calculated load that results in the engineer saying we only need a 200 amp panel here. We have a primary current of 208. Do we have to use all of that? Well, we don't have to. These conductors would generally be sized based on this 200 amp rated device, okay, here. So we would have possibly running down in here, what size conductors would we have here? Well, let's go look at the code and say, what if we wanted to do that? Well, if that's the case, then we would have right here, 200 amps. And that would be a 3/0 right there. So in our graphic, just for argument's sake, these could be 3/0. And this was a 200 amp panel. This has a 208 secondary current rating, and that's fine. Many times we have an oversized transformer, okay, that be able to supply this panel. The load was calculated out, and it didn't need to be more than a 200 amp device right here. So these conductors are 3/0. Now, if I were to do that, would they still meet this tap rule? And let's look at it. Again, primary to secondary was still 2.31. And now what you've got here is, what is the ampacity of these conductors? Well, it was 200 amps. So let's do that. So are we going to be okay? So let's read the rule. It says the primary to secondary ratio, which was 2.31, and we're going to multiply that by 75, and that is 173.25 again. Well, our conductor's good for 200 amps. We are good to go. So that meets the tap rule, right? Now, what about the primary? What if I want this to only be sized to handle the primary current, which is 90 amperes under this tap rule? Okay, the whole purpose of the tap rule is to have a conductor that taps onto a feeder that doesn't have the same ampacity as the feeder, but still is protected at its ampacity. So you've got these rules. So what do we got here? You've got the primary. So what if this was again, we said it was a 90, and we had the 90, and we selected a conductor, and we said that was going to be a conductor for 90, and that was a 3 gauge, and it was good for 100. So this right here was 3 conductor instead of our 2. Well, again, that exceeded the 75, so that was good. So I could have a 3 gauge here, and then I could have a 3/0 here. And that's another example, would be perfectly fine under this tap rule. And everything would be considered protected. No problem at all. Now let's keep on going. Let's keep on going because we want to make sure we meet all these rules, okay? All right, so the next thing says, okay, in order for you to do what we just said you to do and do this application, it says the total length of 1 primary plus 1 secondary, so here's 1 primary plus 1 secondary, excluding the portion of the primary conductors protected at its ampacity, not over 25 feet. So I can take since I've got tap conductors here, and they aren't protected at their ampacity, that's the whole purpose of the tap rule here, is so they run down here, and this is 19 feet, and the conductors then on the secondary go out 6 feet in total. So that is cumulative, that's 25 feet. So the primary plus the secondary does not exceed 25 feet, so far we are good to go under this tap rule. Now let's go on to item 4. It says the primary and secondary conductors protected from physical damage in a raceway or other approved means. Well, this is a raceway. This is EMT. This is FMC, flexible metal conduit, which is also a raceway. If you go look at the .2 description within their articles, you'll see that they refer to them as being raceways. Okay, so that's a raceway. That's a raceway, so we're good here. And then you've got here, which is a raceways as well. Okay. Now the other approved means might be based on its location, based on what wiring method you're using. The AHJ might consider them protecting them against physical damage. Okay, and they'd be perfectly acceptable. Let the AHJ make that call, and you're perfectly fine. Okay. So in our case, we're good to go here. Item number 5. Now, this is where it's going to dictate these secondary conductors also. You keep wondering why I size them based on whatever the load is calculated out and whatever this device is rated at. Then it says secondary conductors that terminate in a single circuit breaker. There you go, single. Or it should say single circuit breaker or set of fuses that limit the load current to not more than the conductor's ampacity as permitted in the 31015 Okay, most notably 31015B16, and of course all the applicable adjustment and corrections if necessary. Whatever this new ampacity ends up being, it has to terminate and be limited to the load by this device. So here, this is 200 amp in our example that we just kind of did a minute ago using the tap rule. These conductors were rated for 200 amps. So it is limiting it to 200 amps. And of course, this output here, the secondary current rating was 208, so everything's going to work good. Now, even if this was 300 amps and we size this for 350 kc mil, again, the calculated load might be much less than that 300 amps. And because you do have a transformer that has a limitation here, the secondary is 208 amps, okay? But it is still, these conductors would be, based on the rule here, or would be at least limiting the load, okay? Now, we sized them without any tap conductors, and that's how we got 350 kc mil. But under the tap conductor rule, again, whatever the size of this device is that's going to limit the load, then these conductors have to be sized with the same ampacity that can terminate into that device. And we did that. So whether this was a 300, these were 350s, or whether we calculated this out and this was a 200 amp device and these were 3-aught, then we were protecting it and everything was good. And again, remembering all copper unless expressed otherwise. So that's our not more than 25 foot primary plus secondary. Primary plus the secondary cumulative doesn't exceed 25 feet. Now, what's this one over here? Now, this is all the same applies except for this little rule here. Now, this little rule here says, okay, this total length here, all right, if the primary portion right here is actually protected at the ampacity, okay, then at its full ampacity, then the 25-foot portion doesn't have to start until the secondary. So this could be any length. It doesn't really, there's no limitation here, okay, theoretically. I mean, you have voltage drop, you have all those other limitations, but they're not mandated by the code. They're good design practices, but not mandated. Now, fire pumps and things like that do have voltage drop rules and things like this, but we're just talking general here. So here, these conductors going down, but the 25-foot limitation is going to be used here, okay? And this would be the secondary. All right, so the total length of one primary plus one secondary, excluding the portion of the primary conductors protected at its ampacity, should not be longer than 25 feet, okay? So if these were 4-aught, let's say, and they're protected at 225, and these conductors that are feeding the primary are also at 225 amp, or these are also 4-aught, then they are protected by this by this device here. It's protecting this feeder. It's also serving as a primary protection as well. And it also means that since this is being protected at its full ampacity, then these secondary here could go up to 25 feet. And I can apply the entire tap rule to that portion of it. Okay? And that's how it's going to do it. All right, so that's just the basic general without getting it too complicated. That's the whole rule here that applies to that. Now, you still have to meet all these other rules. These conductors, again, would have to be at least a third the rating of the primary, the feeder, the overcurrent device is protecting the feeder, and it would be, obviously, if this one was, this one was, if it's full size of this feeder, and all that type of thing, okay? So that's kind of how that rule applies, but this can be very beneficial. If you have, let's say, in this case, this is your primary overcurrent protection device, and these transformers are all located within sight in the same room. If they were not located within sight of the disconnect, then we'd have a label on here, and it would say remote, and it would say where it's at. But here they're all in the same room for this example. Now this panel might not be. That's why that extra 25 feet might be beneficial to you. Okay, but all of this is, say, located in a transformer room, and this might go out of the transformer room, and that's why you need that additional 25 feet. This tap rule can be your friend. As we said, whether you're applying the tap rules here or you're applying them here. Okay, keep that in mind. Now, what about this device here? This can also, like we said, can also be rated at 250% because I got multiple transformers. All right, and we follow the transformer rule. Now let's look at the code rule and see why would we want to utilize this at 250% when we've been doing everything else at 125%. Well, here's what it says. Remember, the table in 450.3b says that I could go up to 250%. Well, why would I want to do that? Well, 250% rated primary protection has a more common and widely applicable advantage. It's in making it possible to feed 2 or more transformers from the same primary feeder. Okay, the number of transformers that might be used in any case would be dependent on the amount of continuous load on all transformers. Well, obviously, we have to size that feeder. We have to know what the continuous loads are. Okay, so it is going to be a limiting factor of the number of transformers that you can run. But once you assume that, in all cases, the primary protection must be rated not more than 250% of any one transformer if they're all the same size, or 250% of the smallest transformer if they are of different sizes. Okay, we'll stop there real quick so I can explain that. Well, since I can't exceed 250%, if I have 2 transformers that are the same, and I can take their primary rated current and do that at 2.50 or 250%, then I know that I'm not going to exceed it because they're both the same. They have the both same primary current. But if I had 2 transformers that are tapping a feeder, and one is, say, a 50 kVA and one's a 75. If I utilize the primary current from the 75, then I'm going to actually exceed that of the 50 kVA transformer. So that protection is going to be more than 250% because I'm going to base it on the primary current of the 50 kVA transformer, and I'm going to have a problem there. So I always want to use the lowest one so that I know that I don't at any point exceed 250% for the primary protection on the weakest link or the smallest transformer in the string, if you get what I mean. So that's what we mean by that. Okay, so let's keep on going. Now, for each transformer fed, there must be a set of fuses or circuit breaker on the secondary rated side rated at not more than 125% of the rated secondary current. All right, and we did that in our calculation. We did it at 125%. And so we don't have to exceed it. Remember, I don't have to use the 125. Again, in our case, we did it and got a 300 amp overcurrent device to protect the secondary. But like we said, what if our calculated load resulted in a 200 amp panel and had a 200 amp main breaker and it was a 200 amp device? Yes, that can still protect the secondary because I could have gone up to 125%. I just chose not to. And so my load calculated and all I needed was a 200 amp panel. I sized those secondary conductors based on 200 amperes, which in our case was a 3/0. And so then the secondary current rating was 208 amps, so it could easily handle the 200 amps. So that wasn't an issue. And under the tap rules, we were perfectly fine. Okay. So that's a great example of how to use the tap rule. Okay. But in all cases, that primary overcurrent protection device can exceed 250%. So let's go back and examine that and make sure we're okay in our rules here. So here's what we did. So in our overall example here, we had a 225. So again, these both are 75. Okay, so we take that there was 75 kVA, and we calculated what the primary current was, which again we said was 90. And we take that times 2.50, and that is 225. Well, that's the design we chose, and that is a common breaker rating under 240.6a. So we were good to go there. We sized conductors to that. They're all protected. We already did everything else, and we know that the tap rules worked fine. So at any case, we did not exceed 250%. But because of the load on this transformer and the load on this transformer, due to the potential inrushes from these, and now these conductors are protected on this one, and these are protected on this one, these feeders are protected. This device limits it by protecting it at 225 amperes, and we're not exceeding the primary protection of 250%. So it is actually protecting the primary of these transformers, and each one of these transformers are protecting the secondary based on their individual protection in each panel board, which is also meeting the requirements of 408.36 as well for protecting the panel board as well. Okay, so this is a truly compliant installation. All right, and we've shown you 2 ways to meet the tap rule here. And I've even shown you a way to use the tap rule here that might get you out of a predicament. Okay, all right, so let's come back to me. Hey, transformers can be complicated. You just need to take your time, work through it. If any of this was confusing to you, I apologize in advance. It's confusing to everybody. These are tap rules. We haven't even got into the secondary conductor sizing rules, which can also be utilized. Okay. But this is a tap rule application here. All right. So if you have any questions, as always, feel free to email me at info at masterthenec.com. Okay. Down in the ticker below, you'll see the website that you can go to watch more of our videos. You can subscribe to our YouTube channel. You can listen to our podcast. Go to our YouTube, our Facebook channel. We have a closed group. If you're an electrician or an engineer and you're trying to study more, prepare for an exam, you're engineering PE, or you're trying to do something or to become an electrician, or you're an apprentice, join that private group. Because you're going to get a lot of information there that's shared, that's not open on the internet. It's private. It's within that group. We also have a regular area in our Facebook page that you can still post your questions, but everybody gets to see them. So if you're kind of a little bit self-conscious about asking a question, then you might want to get into the group. But if you want everybody to be able to chime in, again, it's all moderated. I am going to look at the question because I don't allow bashing. It's not a democracy in my forums. Again, you're free to have an opinion, but you're not going to take us off track because we need to focus on answering the question. And your opinions are important, but if they are potentially a safety concern, then we're probably going to not allow it. So don't get offended, okay, if that's the case. We're here to try to teach you. So hopefully you got something out of it. God bless. Until next time, stay safe. And hopefully this episode has really helped you with sizing conductors, because I've given you a lot of information here. How to use a tap rule, how to size it without using the tap rule. And so it's really important. If you don't understand it, reach out to me. If you disagree, hey, it's okay. You can disagree with me. I'm not perfect, but I am trying to help you get better with the code. So thanks again. Until next time, stay safe and God bless.